Today, we're scheduled to have that first quiz, and I said we're just going to skip it because we haven't covered enough material yet. I have these, like my version of what would have been the quiz today if we had one. So I'll hand that out toward the end. You can take it, see how you do on it. I think maybe then hang on to it, and and I'll just go over the answers at the start of class next time. So you can just sort of see like what kind of things I want you to look for in the notes and that kind of thing. Okay? Yes? No. Yeah. And did everybody get a chance to at least start those problems on, what was it, the introduction problems? So I already had one question, or a couple of questions about number 2. That's the one where you have this box and you're pumping it up and lowering the pressure inside and that kind of thing. So I'll go over that a little bit. Does anybody have any other questions on any of those problems? Yeah. Okay. Okay. Oh, okay. Okay. Is it wrong? Okay. We'll find out. All right. So so on introduction number 2, this is the one where you have a box, and it doesn't give any length. It must. Oh, okay. Oh, we did part of this in class, I guess, didn't we? So all of the lengths are 0.35, and you increase the internal pressure to 100 psi gauge pressure. And I guess to go from pounds to square, I mean, you can just look that up. It's not like unit conversion is an important part of this class or anything. So you can just Google how to, the conversion. But to go from pounds to go from, let's see, 100. Let's do it as pounds per square inch, and we want to get that into newtons per meter squared. A newton is about, I can't remember exactly, it's like 4 point something pounds, or no, a pound is something like 4 point something newtons. Let's see, what do I know here? Let me just Google. I'm just going to Google newtons per pound. Okay, 4.448 newtons is a pound. So I'm going to use that as a conversion. Well, instead of 100, let's just do this. Let's just do a conversion between PSI and Pascals. So 1 pound is 4.448 newtons. And 12 inches is 1 foot. And 12 inches is 1 foot. And so, if you cancel this stuff out, the pounds cancel, the inches cancel there and there. So now if we multiplied this out, we'd have newtons per square foot. We don't want that, but I went this direction because I happen to know how many feet there are in a meter. So 1 meter is 3.281 feet. And now the feet cancel. And the units we're left with are newtons per meter, newtons per square meter. And so if we multiply that out, that gives us that 1 PSI. Can someone multiply these numbers all out? 4.448 times 12 times 12 times 3.281 times 3.281. $6,000 what? 726. Okay. Let's get a couple people to do it, and then we can get a verification. I don't actually know even what the ballpark of this is, but I think it should be bigger than 1. Okay, great. 6895 pascals. So now in the future, you can use that as a conversion anytime you want to. Or you can always just Google, if you want to convert 100 PSI, just type in 100 PSI in pascals and it'll spit it right out. Google will spit it out for you. Okay, and so that says that 100 PSI is 689,500. This should say 100. And 1 atmosphere of pressure is 1 point, oh, well, it says to use 14.5. So what's 14.5 times 6895? $99.99 what? 978. Okay, so it says that on the inside of the box, the gauge pressure is 100 psi. So the pressure inside is 689,500 plus the atmospheric pressure. Oh, wait, I don't. Oh, yeah. Okay. Plus 99,978. And so what do you get when you add those together? Seven, 8, 9, 4, 7, 8, and that's in pascals. This is the absolute pressure on the inside. Okay, and then I think just one by one you're going through and figuring out the forces. And you asked, aren't all the forces the same on all the different faces? Well, they all do have the same magnitude. You're right about that, but they're different directions. Um, because so pressure is not a vector, but force is a vector. So you need to make sure that you know the direction that that force is pointed. And in every case, it's just perpendicular out of the box. Okay, it's perpendicular into whatever the boundary is. So the net. Okay, so let's do one of these. So free body diagram of face 2. So that has a force of 99978 times the area of that face, which is 0.35 squared. And coming the other way, there's a force of 789,478 times that area. And so calculate those forces, and then those arrows give the direction. By the way, if you, so you can see that those two numbers are different, right? So how is it that this box isn't accelerating if those forces are different? Well, this isn't all the forces yet, okay? You also have forces if you think of where the, where this is welded. You have forces like a distributed force all the way around the edge, keeping this thing from flying apart. Okay, and until it explodes, this force, this total force plus this has to equal this one. Okay. Eventually, this force gets too big if you keep pumping it up, and the weld joint breaks and the box explodes. But you could use this if you figure out what the surface area of contact is of this surface, the surroundings. You can figure out how strong that connection has to be, That doesn't have anything to do with this problem, but just for sort of understanding what's going on. That's like the thought process that you have to use in a lot of problems in D-form. And a lot of you will probably take that. Okay, so that's number 2, and then number 6. Okay, so you have this, like if you think of the gas in this cylinder as our system, then our system is something like the black thing there. And we have some areas, we have the atmospheric pressure, and we have a 200 Newton force pushing down. We also have a force pushing down of 1.01 times 10 to the 5th pascals times that cross-sectional area, which is pi times 0.05 squared. And you know what? Let's not use this as the system that we isolate. I am going to keep those two forces there. But let's isolate the, we'll think of isolating the piston itself. Okay. And so what's the force on the other side of the piston? That comes from the pressure of the gas. It's the same area, but it's the pressure of the gas times pi times 0.05 squared. In equilibrium, the two going down have to equal the one going up. So we have 1.0, you can think of this as Newton's second law, 1.01 times 10 to the 5th times pi times 0.05 squared plus 200 is equal to pi times 0.05 squared times t. And now you can just solve that for p. Can someone calculate that? $126,464. Okay, so in order to support that additional force of 200 newtons, which isn't a very big force compared to these other forces, you just need the pressure of the gas to be a little bigger than atmospheric pressure. That makes sense, right? The harder you push down on this thing, it increases the pressure on the inside. If this piston was in equilibrium without that 200 newtons, it would just be exactly atmospheric pressure. Okay, so is that absolute or gauge pressure there? That's absolute. Really the easiest way to think of whether something's absolute or gauge is just think like the only time we're ever going to use gauge pressure in this class is if a measurement is given to us and it says that it's a gauge pressure. Okay. What we want to use is the absolute pressure for every calculation. Okay, so this is the absolute pressure. And now we know that so that's part B. To get part A, the absolute pressure is the gauge pressure plus the atmospheric pressure. And so 126,464 is equal to the gauge pressure plus 1.0, I'll write it in the same notation as the other one, plus 101,000. And so P gauge is 25,464 pascals. So if you had a pressure gauge, and you were measuring the pressure of the gas inside there, this is what it would read. But that's because it's comparing it to atmospheric pressure. And so you just need to remember that the pressure that's read off the pressure gauge, you always need to add in that atmospheric pressure unless you're told otherwise. Any questions about that one? Any other homework questions? Yeah. Last Thursday. Really? Okay. Oh, I think maybe I didn't have, it wasn't, yeah, I think that's the problem. So you can just go to the notes, go to the old lecture notes and just, you can read that stuff off from last year. So sorry about that. That's a little bit of a hassle, but it works now, so I'm happy. Okay, so the next thing that we need to talk about, really we'll be talking about this for a long time, is the first law of thermodynamics. And this is just a statement of conservation of energy. In Physics 1, conservation of energy looked something like the change in, so you might not have used the delta sign or the E or whatever, but what you were using was essentially the change in energy of your system is equal to W, where E was the sum of the change in kinetic energy plus the change in potential energy. Well, the change in energy was the sum of those changes. And W was all the work done on the system, on the thing that you're isolating, by all the non-conservative forces. Non-conservative forces. So we need to be clear on what conservative and non-conservative forces are. How does potential energy relate with work? Now, one thing that, anybody remember what the work energy principle is? I think I might have asked this a couple days ago. So the work energy principle is where conservation of mechanical energy came from. And it's a more simple statement than this. It doesn't have any potential energy in it. And it just says the work done by all the forces on the thing is equal to the change in kinetic energy. Okay. So if you do a bunch of work, you speed the thing up. Okay. That's a really simple statement. It's easy to understand, but it can be a little harder to do the math because calculating work can be a pain. Work is defined in terms of an integral, So when we can avoid using the definition of work to calculate work, we'd like to. And that's where potential energy comes in. The change in potential energy, you can think of that as just a clever, easy way to calculate the work that's done by conservative forces, okay? That's what the change in potential energy is for. So we don't have to use the integral definition of work for any conservative forces. Okay, so what's a conservative force? Anyone remember? Yes, that is one. Anyone, and that's the most important one. Anyone remember the definition of conservative forces? That's right. So a conservative force is a force that that only depends on the location of the object. And it doesn't even have to depend on that. But if knowing the object's location is enough to know what the force is on it, then that force is conservative. Okay. So these are forces that only depend on the object's location. All right, so if the isolated object, the system, is the stapler, once we've measured the mass, okay, so we'll go into this knowing the mass of this thing. And now, if I put it here, do we know the force applied by gravity to it? Yeah. Here? Yeah. Anywhere we put it. That's enough information to know the force gravity applies. And it doesn't matter what path you take to get there, gravity is still going to apply the same force to it. Okay? So that's what a conservative force is. And gravity is the most important conservative force. So what about non-conservative forces? You know, maybe that's true of every kind of force. Well, think about the friction force on this as I slide it. So let's take a picture of this right as it gets a foot from the edge, okay? And I'm sliding it this way. Snap, that's the picture. So what was the force of friction on the stapler when it got to that location? Well, we don't know the magnitude, but we do know that since it was sliding this way, the direction's that way. Okay. And now I'm going to slide the other way through the same location. Quick. Okay. What's the force of friction on it as it got to that point? It's the opposite direction, so they can't be the same. So friction is a good example of a force that's non-conservative. Telling you where that stapler is not enough to know what the friction force is. And a lot of other forces are that way too. The normal force, so it's sitting here right now, the normal force is pointing straight up and it's small. If I push down here, the stapler is still in the same spot, but now the normal force is bigger, so that's not conservative either. So conservative forces, it's a pretty stringent requirement. There aren't a lot of things that act this way. Here are the most important ones that do. Gravity. Elastic forces. I'm going to just say spring forces, but really it's true of any elastic materials. Electric fields, magnetic fields, probably some others, but those are the most important ones. And so we have this definition of conservative forces, but why do we care whether something's conservative or not? Conservative forces have potential energy fields, or let's say have potential energy functions Um, and the work done by a conservative force is just equal to the negative change in the potential energy. Okay. And that's way easier than calculating the work using the definition of work. So this is much easier than using work is the integral over the path an object takes of the force vector dotted with the increment along the path. Okay, that's the definition of work. It's a line integral. Sometimes you can simplify it, but in general, you just would prefer not to have to deal with that. Okay, so anyways, that is the reason that we, so why don't we just use the simple idea that the energy is the kinetic energy, work is the work done by all the forces. Why would we instead define the energy of the thing as the kinetic plus the potential? It's so that we can avoid having to try to calculate the work for all of these conservative forces. All right, so, the kind of examples, well, and you use this in, so in physics 1, I mean, this is probably like the first problem you did. I know you did problems a lot harder than this, but if you have a skier who's at the top of so here's a skier at the top of a hill, let's say it's 5 meters high. And the skier starts at rest. If it's frictionless, what's the skier's speed at the bottom? And we know we're going to use this equation that says the change in the skier's energy is equal to the work. And we can write that as the change in kinetic energy plus the change in potential energy is equal to the work done by non-conservative forces. What forces are acting on the skier at some random point going down the hill? There's 2. Gravity and normal. And I just said that normal is a non-conservative force. Anyone know how, like, to what extent do we have to treat the work done by the normal force in a problem like this? I mean, when you've done problems like this, you don't include any work done by the normal force. Maybe the question is, why is that? So that's why you don't have work done by friction, but you still have a non-zero normal, and it's non-conservative, so you should have to include work done by the normal force. Yeah. It doesn't do any work. That's exactly right, because at every instant, the path that the person is on is perpendicular to the normal force. And any force that's perpendicular to the path at every instant does no work. And so basically, like normal force, you just get really lucky with. You get normal force for free. If that weren't true, then energy would be a lot less of a useful approach for problems like this. Okay, so at the top and the bottom of the hill, the kinetic energy at the top, he's starting from rest, so that's 0. The potential energy, if we, so remember the function for potential energy is mgh. If we say our height equals 0 point is at the bottom of the hill, then this is equal to, what did I say, 5 meters? So this is equal to the mass times g times 5. And then at the bottom of the hill, the skier has some unknown speed. So we just have to write that as 1/2 mv squared. We'll try to calculate that speed. And the potential energy is mgh, but this time h is 0, so that's 0. And so the change in kinetic energy, so if I write this as change in kinetic plus change in potential is equal to the non-conservative, the work done by non-conservative forces, this is 0. The change in kinetic energy is 1/2 mv squared, the later kinetic energy minus the earlier kinetic energy. The change in potential energy is 0 minus 5 mg, and that's equal to 0. Divide both sides by m, and you can cancel that out. And you get that v squared is equal to 10g. And so the square root of 98.1. Can someone calculate that? Like 9.90? Okay, meters per second. Okay, so that's the way you did problems like this in Physics 1. In this class, I mean, it's still conservation of energy, but we have to deal with a couple of new things, and we have to deal with a new sign convention. So now we have to include heat. That's the change in energy due to a difference of temperatures. Okay, we didn't have to do that with skiing problems because we assumed there was no significant thermal energy changing. We have to deal with internal energy, which you can think of as energy that an object has resulting from its temperature and its pressure. So again, we didn't worry that we didn't in Physics 1 think about the skier's temperature or pressure changing significantly enough to matter. And we have the new sign convention where W is the work done by the system on the surroundings. Okay, so this right here is just a summary of how things change compared to what they were in physics 1. It's not very many things. It's just those 3 things, you know. We have to deal with heat, we have to deal with internal energy, and we have to deal with this new sign convention. And those are the only things that change. So the first law of thermodynamics with these 3 changes says that the change in energy is equal to the energy added to the system by heat minus W, because of the sign convention, where the change in energy is equal to the change in kinetic energy plus the change in potential energy plus the change in capital U, which is internal energy. So this is the first law of thermodynamics. Okay, so remember this one. This is, you can skip everything else I said, just remember this. Heat. So that's the energy added to the system by heat. And heat is a change in energy produced by a difference in temperature. This U is the internal energy. So if you take a tin can of stewed tomatoes and put it in the microwave for 8 minutes, don't do that. And turn it, I don't know, 8 minutes, it wouldn't last that long, but put it in there for a little bit and it'll wreck your microwave, but it'll also increase the temperature and pressure inside the can, okay? And so if your system is the stuff inside the can, okay, what happens to the energy of your system? Well, the kinetic energy doesn't change. It's still just sitting there. The potential energy doesn't change because its height doesn't change, you know, so it doesn't gain any gravitational potential energy. But the internal energy increases a lot as you increase the temperature and pressure, okay? We couldn't consider a case like that in physics 1. That's what we've added now. Okay. Any questions about that yet? Okay, so, and Q is the heat. In everyday language, you think of heat as related to temperature, kind of. It's a temperature thing. But remember that in physics, heat is energy. It's a change in energy that's caused by thermal things, temperature-related things. Okay. now I want to give some equation for types of work that we're going to see pretty often. There are 3 of these, I think, that I'm going to give you. The first one is work done by changing the boundary, the system boundary. So I'm going to give you the results, and then I'm going to show mathematically how it comes about in sort of a limited case, but it gives you a sense of why this works. The work, when the boundary changes, is equal to the integral from the starting volume to the ending volume of the pressure of the system, dV. Okay, this is a totally general result. This is if your boundary is a plastic bag and it shifts around a little bit, this equation works. It's just calculating that integral is a pain. But am I gonna? Well, yeah, so let's think about it. This is like a proof in, the limited case of a piston and cylinder. Okay, so I'm not proving that it's totally general, but it gives you a sense of where this comes from. So let's say that we have this piston, cylinder, and this is what we'll call the height h at any instant. Okay, this is the gas. Well, W is the work done on the surroundings, right? That's the sign convention we're using. Okay, all that is the gas. And so the work done on the surroundings, we can think of as the integral as the piston. I mean, the only place that gas can do any work is on the piston, because the other walls don't move. You can't do work if there's no motion. Okay? So the only place we have to think about the work is the work that the gas does on the piston, as that piston moves from a height like h1 to height h2. Okay? So it's going to be the integral as the height goes from h1 to h2 of the force that the gas applies to the top. And that force is the pressure times the area, the cross-sectional area. And then dH. Are you with me on that? This is the force applied to the piston by the gas pressure. So if you have a force, if you have a pressure that's acting over a certain area, the total force that it applies is that pressure times the area. So that's what that PA is there. Okay. And now if you group it differently, you get that W is equal to the integral from H1 to H2 of the pressure times the quantity AdH. And AdH is just, you can think of that as the change in volume. That's the only way the volume can change. And so this comes out to be the integral from the starting volume to the ending volume of PdV. One thing I want to say about this is it's always nice when this happens. It means you don't have to think about stuff as much when you use it. You can trust the sign that you get out of this. You don't have to think physically about whether that work is going to be positive or negative. You do this calculation, W is what you get out of that integral. Okay. And the effect is, notice, if the system expands, work is positive, and if the system contracts, work is negative. So that always gives you a way to sanity check your answers using this. Okay, you do the integral. So say that you have a gas expansion and you want to calculate the work that's done. Okay, so it expands, so you know that your final answer is going to be positive. Then you go through the long integral, you get an answer that's negative, you know something went wrong. Okay. So this is helpful as a sanity check on answers. Okay, so let me do an example problem. So let's say that there's a gas pressure of 1.30 times 10 to the 5th pascals at a volume of 0.35 cubic meters. Then the temperature of the gas is reduced as the pressure is held constant. And so what would happen to the gas if you did that? So you're going to keep the pressure constant and you're going to reduce the temperature. Is the gas going to expand or contract? It's going to contract, yeah. So the volume reduces to 0.2 cubic meters. What's W for the gas? For this process. Well, we know that W is equal to the integral from volume 1 to volume 2 of P dV. And we know the two volumes. We're starting out at 0.35 and we're ending at 0.2. The pressure is held constant, so over this whole integral, that pressure is 1.3 times 10 to the fifth, and then we're taking the integral with respect to volume. And if you go through all that, you can pull the constant out, take that integral, and you get negative 19,500 joules. Does that negative make sense in this case? Yeah. The volume decreased, and so the work has to be negative. Okay, so what about the fact that that pressure stayed constant? So this is super easy if you have a constant pressure, but what if that pressure, like in most cases, as you're changing the temperature of the gas, that pressure is varying over the whole thing? Well, then we would have a problem unless we know a relationship between the pressure and the volume at each instant, okay? So in a constant pressure case, this is really easy. If we don't have constant pressure, in order to do this integral, we at least need to know what the pressure is as a function of the volume, okay? So in order to compute this integral, for W, we need to have a relationship. Pressure is a function of volume. Constant pressure is especially easy. That's, if you see one of these and you have constant pressure, you're happy. Or like I'm trying to save you time on a test or something. So constant pressure is especially easy. So that's important. Any questions about any of that? All right, the other two, if you remember, I mean, I've been talking about this for a long time, but I'm giving you three types of work that we'll see a lot. This is by far the most common, but I'm going to give you two other types too. So the second one is if there's a rotating shaft interacting with the system. This is pretty common because a lot of times our system will be the insides of a motor, and this is how motors do work on their surroundings, okay? Or you could have a motor connected to your system, and the shaft from the motor is doing work on your system, okay? So this will mostly come up if there's a motor involved somehow. So I'm going to break this up into two pieces. This one, you don't want to trust the sign. You just need to think physically about what's going on. So if the system is, your isolated system is doing work on the surroundings, and that would be like, for example, your isolated system is a motor. Then the rate of work is equal to the torque that's applied to that shaft times the angular velocity. And if the opposite is happening, so B, if the surroundings are doing work on your system, like for example, the motor is outside of the system boundary and the shaft is acting on your system, then the formula is the same except it's negative. So negative torque times angular velocity. Yes, so that's important. So when we were talking about the work done by expansion of a gas, it gave us an amount of work. This is the rate at which work is done on the surroundings. And that's what we're going to see with the next one too. So if you wanted to use this in the first law of thermodynamics, you'd have to integrate it over time or something like that. Okay. Or the other option is in a couple classes, we'll get into the differential form of the first law, and then you can use it in this form. But right now, in that form, it's not compatible with the form of the first law that I gave you. And then the other type is electric power. And there are really two ways that we can have electric power interacting with our system. One is our system can be the inside of some electrically controlled thing. And so the cord comes in and electric power is done on our system to make the other stuff happen. Or our system can be like a turbine or something and be generating electric power that's used outside. Okay. So again, I'm going to break it up into A and B, just depending on whether our chosen system is using outside electric power or whether it's generating electric power for the outside. So A, if the system is using outside electric power, then the rate of work done, W dot, is negative voltage times current. And again, just like with the rotating shaft, the other option is that, you know, the system is generating power for the outside. And in that case, you just have positive instead of negative. So if the system is supplying electric power to the surroundings, then W dot is equal to positive voltage times current. And just like before, notice that this is a rate. And so you have to do something with these before you can use them in the first law of thermodynamics the way I have it written. So what do we have so far? So we have an expanded, I'm going to give you an expanded everything. So all these different things that we have the ability to calculate, I'm going to substitute them all into the first law and see what the ugliest looking but most exhaustive version of the first law is. So the expanded version of the first law so far. Well, the simple version, I'll start with that. The change in energy is equal to Q minus W. But the change in energy is the change in kinetic plus the change in potential plus the change in internal. So let's first make that substitution, those substitutions. So, all right, that is, so the change in kinetic energy you can think of as 1/2 times the mass times the change in the speed squared. Okay, that's the change in kinetic energy. And then we have the change in potential energy, which is mg times the change in height. And then we have one that we haven't expanded at all yet. We haven't talked about how to figure out the internal energy or anything. We'll get to that eventually. So for now, that's just the change in internal energy. And all this is equal to, we haven't talked about heat yet. So I'm just going to leave that for now as Q. And now W, we have minus the integral from volume 1 to volume 2 of P dV. And then we have minus plus the integral of Q, I'll call this, sorry, not Q, this should be W. W dot due to a rotating shaft, dt. Running out of room. Minus plus the integral of W dot electric dt. And I did those as minus over plus because we're subtracting all the works. So if W is equal to, if W due to electric power comes out positive, you need to subtract it there. Okay, this isn't the final form yet. I mean, because we still have to talk about internal energy and we have to talk about Q, but with everything that we've figured out so far, you could just plug what you know into this equation and it would work. Anybody have any questions about this yet? Okay, so one of the problems I'm going to assign asks you to use this new version to basically do another one of those sphere problems. Okay, and what I want you to just keep in mind is all of this, like in physics 1, you couldn't use this equation. You would have just had a lot of terms be 0 in every problem. You wouldn't be dealing with internal energy, that would go away. You wouldn't be dealing with heat. You wouldn't be dealing with changes in boundaries. Okay. And you would have just had non-conservative forces. So you've seen this equation before. We just have a lot more terms in it now.
Well, this basically just allows to, instead of using a frictionless surface.
Well, the original, if you go all the way back to when I first started talking about this, oh yeah, thank you. This is what you had in physics 1, and you could put, if you knew the work done by the friction, you could have put it in there. But what this lets us deal with is changing boundaries, temperature, various types of temperature effects on things. It's mainly, so it's the changing boundary of a deformable thing in addition to like thermal effects, basically. Any other questions right now? Okay.